Okay, so our second talk here today is by Walter Parry, and he will tell us about a computer program that he wrote to compute some things for Thurston maps, if I'm not mistaken. So Walter, please.
Thanks very much to the organizers for inviting me to give a Quasiworld talk. Here we go. We're dealing with a finite branch cover F from the two-sphere to the two-sphere. F has exactly 4 post-critical points, lowercase a, b, c, and d. We're thinking of the two-sphere as a square pillowcase. So the two-sphere has a cell structure with vertex set, the post-critical set. We have 4 vertices in our cell structure and 4 edges forming a quadrilateral, as we see here in the picture. We get, therefore, two cells called tiles. Okay, we have our square pillowcase here, and our map F pulls back the square pillowcase to give us another cell structure on the two-sphere called the lift complex. The tiles of the lift complex are colored by the colors of their images, and the vertices of the lift complex are labeled by their images. So, for example, this vertex maps to post-critical point B. Let's now discuss liftables. So let G be either the modular group, the pure modular group, or the extended modular group for the square pillowcase. Let's let phi be a homeomorphism of the square pillowcase representing an element of G. We say that phi is G liftable if there exists another such homeomorphism, phi tilde, representing an element of G, such that phi circle F equals F circle phi tilde. We have a commutative diagram like at the bottom here. The map phi lifts to phi tilde via the map F. Okay? That's what it means to be G liftable. Simple closed curves in our square pillowcase, which are neither peripheral nor null homotopic, all have slopes. Here are a few examples. The edges of the square pillowcase, which are horizontal, are core arcs for simple closed curves with slope 0, such as this one. Here's a simple closed curve. It has core arc, the bottom edge of our square pillowcase. It has slope 0. The vertical edges of the square pillowcase are core arcs for simple closed curves with slope infinity. And we also have here a simple closed curve with slope 1. Once we have slopes in our map F, we get a slope function. The slope function is denoted by mu sub F. It's a map from the extended rational numbers to the extended rational numbers together with a special element called the non-slope. Q hat is the extended rational numbers, Q union infinity. So here we have Q union infinity, all possible slopes, and that maps to Q union infinity together with this extra element called the non-slope. Mu F is defined as follows. Let's let S be an arbitrary extended rational number. There exists a simple closed curve gamma in our square pillowcase with slope S. Let's pull back gamma by F and look at all the connected components. Gamma 1 through gamma n are all the connected components of the inverse image, indexed so that the first k of them are exactly those connected components which are neither peripheral nor null homotopic. It's possible that there are none of the latter curves. It's possible that every connected component is peripheral or null homotopic. That's the case in which k is 0. And in that case, the slope function is simply defined to be the non-slope. This is the reason for introducing the non-slope. Otherwise, if there really are curves which are neither peripheral nor null homotopic, in which case k is positive, then the slope function is the common slope of all of these connected components. All these connected components which are neither peripheral nor null homotopic must have the same slope. And we define the slope function value at S to be this common slope. Moreover, suppose that the connected component gamma I maps to gamma with degree di. Then we define the Thurston multiplier of our slope S to be the rational number m over n, which is the sum of the reciprocals of the degrees of the first k connecting components. So we're only summing over the connecting components here, which are neither peripheral nor null homotopic. And we get this rational number m over n. Now, if the denominator n is exactly the least common multiple of all of the degrees, so now we're considering all of the connecting components, then we say that this rational number is the unreduced multiplier of S. The program PF4 calculates unreduced multipliers of slopes. Okay? A few words about Teichmuller space. We take Teichmuller space for the square pillowcase to be the upper half plane H. We augment it with the extended rational numbers. So H star is augmented Teichmuller space. In this context, we think of the extended rational numbers as cusps, whereas before we viewed them as slopes. The pullback map sigma f is a function from this augmented Teichmuller space to itself. That's the Thurston pullback map of f. Now we come to an unfortunate inelegance, which is as follows. Slope S does not correspond to cusp S, but instead to cusp minus 1 over S in the following way. Suppose S is an extended rational number, and the slope function of f takes S to an extended rational number, not the non-slope. Then this extended rational number is minus 1 over the pullback map applied to minus 1 over S. So it would be nice if the slope function were equal to the pullback map restricted to the set of cusps, but they are not equal. They are conjugate by the negative reciprocal function. Okay? This brings us to the half-space theorem. The half-space theorem appeared in a paper by Jim Cannon, Bill Floyd, myself, and Kevin Pilgrim. It goes as follows. Let's let S be a slope. So S is an extended rational number, and the slope function value at S is not S, and it's not the non-slope. So the slope function takes S to an extended rational number, but S is not a fixed point. Then there exists an effectively computable half-space H inside the upper half plane, such that H contains no fixed point of the pullback map. We gain some control over the fixed point of the pullback map in this way. Furthermore, let's think about the boundary of this half-space H. Let's intersect this boundary with the boundary of the upper half plane, the circle at infinity, and we get a closed interval. The interior of this closed interval contains minus 1 over S, but not the negative reciprocal of the slope of an obstruction for F. So in this way, we have excluded, we have an open interval and a non-empty open interval on the circle at infinity that contains the negative reciprocal of our original slope, but it excludes all negative reciprocals of slopes of obstructions. This leads us to say that this interval is a half-space theorem excluded interval. It's a half-space theorem excluded interval. And more generally, let's say that an excluded interval is a connected union of these. So excluded intervals exclude negative reciprocals of slopes of obstructions. So this takes care of, we get neighborhoods of all extended rational numbers except for this condition. To deal with this, we have the extended half-space theorem. The extended half-space theorem appears in the Fickle-Phipps paper, where we have F stands for Floyd, and Kelsey, Cook, Lodge, Parry, Pilgrim, and Sands. It goes as follows. Let's let S be an extended rational number for which the slope function takes S to either S or the non-slope. It's the complementary situation of what we had up above, with the proviso that now S is not the slope of an obstruction with multiplier 1. These can be bad guys. Then there exists an effectively computable deleted open neighborhood about -1 over S, which is the union of infinitely many of our half-space theorem excluded intervals. So the extended half-space theorem does not actually produce any more intervals. It just gives us a way of taking infinitely many of those which we already have and getting an excluded interval. So we get an open interval in the circle at infinity containing the negative reciprocal of our slope, such that all points in that interval are excluded from being negative reciprocals of slopes of obstructions, except possibly for this point itself. It's possible that S is the slope of an obstruction with multiplier bigger than 1. Okay, between these two theorems, we have covered the extended rational numbers, essentially. What about the rational numbers? For irrational numbers, I was able to prove that every irrational real number is contained in a half-space theorem excluded interval. We always get every irrational number inside a half-space theorem excluded interval. Taken together, these three results give us an algorithm for determining whether F is Thurston equivalent to a rational map. Here's the algorithm. Enumerate the extended rational numbers. So we have a list of extended rational numbers, and we go down our list of extended rational numbers and evaluate the slope function at them. The slope function computation is very efficient, and as a byproduct, it determines whether or not the slope is the slope of an obstruction. So we go down our list of extended rational numbers. If there is an obstruction, then we will find it after finitely many steps. Suppose there is no obstruction. We calculate slopes, and if we were able to do this indefinitely, we would get a cover of the circle at infinity by these three results. But the circle at infinity is compact. So the computation ends after finitely many steps. After finitely many steps, we get an open cover, and we conclude that there is no obstruction. Questions? That's the end of the preliminaries. So let us look at PF4 itself. In order to understand the program, we have to understand input. And there are two basic ways of inputting information into the program. Here is method number 1. For method number 1, we sketch a lift complex. So that's what we see here in the left. We have a lift complex for a map with degree 3. We have 3 white tiles and 3 gray tiles. We index all of the tiles by distinct integers. Any distinct integers will do. And we label the vertices by their images. In addition to that, so once we have that much information, we have a finite cover from one two-sphere to another. We have to identify these two spheres. So in order to
Walter, quick questions, just to be clear here. So in your picture, this big gray area containing infinity, this is another tile, right?
That's another tile.
Okay.
Right. Our pictures are stereographic projections of the sphere onto the plane. So there's always going to be something at infinity. We might want to put a vertex at infinity, but that's another issue. Okay. Now, so just having the Lift complex vertex labels, coloring of tiles, we get a finite cover from one two-sphere to another. We want to identify these two spheres. So the first step in doing so is to identify the post-critical vertices. In this picture, the post-critical vertices are identified with the larger blue letters. So for example, this is post-critical vertex A, post-critical vertex B, C, and D. Okay, now the program knows where the post-critical vertices are, but there's more to know, and the remaining information is given by a tree. We choose a tree in the one skeleton of our Lift complex with the property that every leaf of the tree is post-critical. It's not necessary for every post-critical vertex to be a leaf, but it is necessary that every leaf be post-critical. In this picture, the tree that we choose is given by the thicker blue edges. So here is an edge in our tree, another one, and another one. We have 4 edges in our tree. This tree provides a kind of frame of reference for identifying our two spheres, and so it's called the reference tree. We have a reference tree with 4 edges. That's what we need for our sketch. So this sketch gives rise to this file over here. This is a standard input file for PF4. All of this text below the word yes is ignored by the program. This text is here to hopefully help the user. It can be deleted or replaced by anything at all. Here's what the input file is doing. The program first wants to know the degree of our function. So the degree is 3. So that goes here. The next block of information is telling the program how tiles are paired across edges. Every row corresponds to a white Lift tile. So this one here is indicating white Lift tile number 1. So we go to white Lift tile number 1, and we traverse its edges, starting with the vertex labeled A. So here's the vertex labeled A in white Lift tile 1, and we traverse its edges in the counterclockwise fashion, and we go to this edge. Across this edge is tile number 4. Next, across the next edge is tile 5, 5, and 5. And that leads to this row of information here. Tile number 1 sees tile number 4, then 5, then 5, then 5. Okay? We do that for all of our white Lift tiles, and we get this block of information.
Sorry, Walter, why do you get 5 several times? I didn't understand this.
There are 5 and 1 have 3 edges in common. So we first go from vertex A to vertex B, and across that edge is tile number 4.
Yeah,
then we go from B to C, right? 5. We always have 4 edges. We must always have 4 edges, and sometimes we get more than, the same tile might occur more than once. Right? Okay. The next block of information here is telling the program where the post-critical points are. So this information right here is saying that post-critical vertex A is in tile number 1, and it has label D. So tile number 1 is here. Here's the vertex with label D. Yes, that is post-critical vertex A. Similarly, post-critical vertex B is at 1B. 1B has post-critical vertex B. And so forth. We do that for all 4 post-critical vertices. Next is the spanning tree, the reference tree T, the tree that spans the post-critical vertices. The program wants to know how many edges, and the number of edges is 4. And now we have to tell the program what those edges are. This 1D is saying that one of the edges is in tile number 1, and it is edge D, the last edge in tile number 1. There's the first edge, then the second edge, the third edge, the fourth edge. That is edge D in tile number 1, giving us this edge of our reference tree.
Just a quick question. So, I mean, you know,
Yes.
before I mean, like index of white lift tile, you gave the indices of the tiles adjacent. And does it need to know which is the first edge in this list or not?
I'm not sure the order of these does not matter. The order of these edges doesn't matter. And
so you don't need to, I don't know, list the I don't know, the neighboring tiles that you go over in a certain. There's no like requirement what the first is in this list.
No.
Okay. Thank you.
No. There's the order of these. The order of this data is irrelevant.
Okay, thank you.
Yes. And furthermore, the tile can be you can use either one. So let's see. So for lift edge 1, we could have said it's 5D, right? Instead of 1D, we could have had 5D. And similarly here for the post-critical points, we could have said, what's this 1D? We could have had 1D. We could have had 5D, yes. Which tile we choose does not matter. Choose any tile. There could be several choices. The label here, though, is fixed, is determined. There could be several choices for the tile, but the label is not arbitrary. Same thing goes here. Order of occurrence does not matter, and we could use either tile. That's okay. Okay, now the program now knows the tree, and it needs a little bit more information. It needs 2 segments inside that tree with the property that the endpoints of those segments are post-critical, and there's no post-critical vertex in the interior of the segment. We want segments to be core arcs. We want to choose 2 segments that are core arcs. These segments cannot be parallel core arcs. So in this tree, this is saying that we're choosing the segment with endpoints A and D. So post-critical vertex A, post-critical vertex D, and yes, the segment in the tree is a core arc, and we decide to say this core arc has slope infinity. Similarly, we chose the core arc with endpoints B and D. So B and D, yes, those 2 edges give us a core arc with endpoints B and D, and we choose its slope to be 1. Okay? And yes,
so this is essentially to sort of find, let's say, the image pillow inside of, let's say, the pre-image pillow. Is that correct?
Absolutely. That's the point. The point is to identify our 2 spheres. The lift complex with its labeling gives us a map, and now we have to identify the 2 spheres, and choosing this tree and these slopes like this give us a way of identifying the 2 spheres. Okay? It's time to run the program. So, before we do that, I should say that over here, well, I guess that's good enough. Can you see this? folder over here. Okay, so this is our input file. That's this file here. This PDF file is exactly this picture here. So now we click on the PF4 icon and this window appears. In order to run the program on our input file, we click on the input file button, we click, and now we navigate to this folder. And by some coincidence, we're already there. So we say we want to open this folder, click. Oh, and now we want the file name. Oh, I'm sorry. I'm supposed to click on the file name. Oh, yes, right. Okay. So now the program has the file and we can run the program. The program just created all of these files and it opened up the main output file. So this file is this file. Okay, so it automatically opens up the main output file and here's what it has to say. Well, we have a Thurston map with degree 3. It's not very enlightening. But already here, we have a list of all the Thurston multipliers which occur for this map. So these 4 multipliers are all of the multipliers that occur for this map. And we have some information. What follows next is some information about the number of Thurston equivalence classes in this Hurwitz class. Next comes information on the half-space computation. So this is some of the numerical results for that computation. And here is a PostScript file with a picture of the half-space computation. We have a lot of half-spaces here. What half-spaces, you might ask? Well, there's a button here called the numerator denominator bound. If we click on this button, we get a dialog box here, and we see the number 25 in the dialog box. This 25 is giving a bound on numerators and denominators, absolute value, of slopes to consider. So the program considers all slopes whose numerators and denominators are bounded by 25. We can put in whatever value we like. And it draws a half space corresponding to those slopes. And that's what these half spaces are doing here. We see that the limits on X are -5 and +5. Why is that? Well, those are the X-min and X-max numbers. So clicking on this button gives us another dialog box. And we see that the values of X-min and X-max are -5 to +5. So these are floating point numbers. We can make them anything we like, giving a valid interval of real numbers. Okay, and so that allows us, for example, to blow up the picture near -1 to see maybe what's going on there. This is numerical data for the same thing. So we see that there's an issue at -1. The half spaces are giving us an interval from -56 roughly to almost to -1, and then from very close to -1 out to +56 essentially. So they don't cover the circle at infinity. And so the half-space theorem does not determine rationality. We must continue with more computations. The supplemental half-space theorem. So what the program does at this point, it looks at these gaps. So there are 2 gaps in this situation. One is near -1 and one is near infinity. Now, given a closed interval of real numbers, there's a unique rational number in that interval with the property that its numerator in absolute value is less than or equal to the numerator of every rational number in that interval, and its denominator in absolute value is less than or equal to the denominator of every rational number in that interval. And the program essentially finds that rational number. And now this rational number might not fall within the bounds that we used for this computation. And so it might be possible that the half-space theorem applies to this rational number. So that's what this is doing here. But more likely, the extended half-space theorem applies to this rational number. That's what happens here. And the program applies the extended half-space theorem to -1, and it gets this interval, which covers the gap. And then it applies the extended half-space theorem to infinity, and it gets this interval. The program writes intervals at infinity like this. So the left endpoint is appears to be 3 2/3, and the right endpoint appears to be minus, what's that, 5/3. So all these intervals taken together cover the circle at infinity, and we conclude that there is no obstruction. This map is Thurston equivalent to a rational map. Okay.
I have a question. Maybe I'm confused here,
Yes.
but you said, I mean, above you had like the Thurston multipliers, and one of them was 3/2. So I sort of, oh yeah, that is. So I sort of thought that this means that the map is obstructed, but obviously that's obviously I'm confused here, but yeah.
Right. If there is a fixed point with multiplier 3/2, then that's an obstruction.
So it's not necessarily a fixed point. I see.
These are not coming from fixed points. These are covering all slopes.
I see.
When we consider all slopes, these are the multipliers which occur.
Okay, I see. Okay, thank you. Mm-hmm.
Right. So this conclusion means that there is no fixed point with multiplier 3/2, right? Well, the algorithm that we just used to give rationality can be generalized. Using smaller intervals, we get a corresponding algorithm for all fixed points, and the program finds all fixed points, usually. And in this case, it says there are two fixed points. One is infinity and one is 1/2. And it turns out that there are even equators for matings. These are mating equators. Okay. We get information on, at this point down here, the program is thinking a little bit about the finite global attractor problem. It's looking at orbits of slopes under the slope function, and in particular, it's looking at all the slopes within our bounds. So with numerator and denominator bounded by 25, every orbit ends in one of these cycles, or possibly the non-slope. So for all of these, for all of the slopes that we gave the program to think about, every one of these orbits ends either in one of these two fixed points or the non-slope.
Oh, Walter, I'm sorry for interrupting you. Just a quick question. With respect to the fixed points, these are fixed points within the bounds? I mean, given the bounds for the
arbitrary fixed points.
These are arbitrary fixed points.
These are all of the
program. Oh, the program is telling us that these are the only two possible fixed points.
Correct. Not just in the bounds. These are all of the fixed points.
All the fixed points. Okay. All right. Thank you.
Right. We're thinking about all slopes here. We're thinking about all slopes here. The only two slopes that are fixed by the slope function are infinity and 1/2.
So let me ask you a question, Walter. So your intervals do not contain any fixed points, right?
These intervals will not, they might, let's see, what do you mean by the intervals do not contain?
Well, I mean, I'm trying to get, can you remind me again, these excluded intervals? So what was special about them?
What they exclude are negative reciprocals of obstructions.
Oh, I see. Okay.
Not just fixed points.
Okay. All right.
That's what's going on up here. So that, you know, the half-space theorem, etc., the extended half-space theorem, there we're dealing with negative reciprocals of slopes of obstructions. So the intervals that we get, you know, let's see. So let's see. See this infinity here, that's a slope. Keep in mind that that corresponds to cusp 0. Over here we have cusps. And so we see that 0 is in one of these excluded intervals, even though this is going to be, this is a fixed point of the pullback map. This is a fixed point of the pullback map right here, corresponding to the fixed point infinity of the slope function.
So what I don't understand is how are you able to find all the fixed points of the slope?
Now, there's, we're using a generalization of this argument. So for the generalization of this argument, now the intervals in question will not contain fixed points. See, you're correct for this computation, for the fixed point computation. So for the fixed point computation, our intervals will not contain fixed points. Whereas before, our intervals were more precisely, negative reciprocals of fixed points. Okay. Okay, that's that. And this main output file always ends with a fundamental group recursion for our function.
So, Walter, just a quick question. Does this also mean that you could compute all the periodic slopes?
No. Okay, excellent question. So look at this statement here. If I understood you correctly, you're asking whether we can calculate all cycles?
Yes. Yes.
Yes. The answer is no. That's an excellent question. So that's what's going on here. So we have to interpret this statement exactly as given. No non-trivial cycles were found. The program does not, I don't know how to calculate non-trivial cycles. And the program spends some time searching for cycles, but in this case, it didn't find any. I don't know. So there's a question for the audience: how to calculate cycles which are not just simply fixed points. Maybe more to the point would be the following question. Given a Thurston map with 4 post-critical points, obstructed or not, is there an upper bound on the length of a cycle for the pullback map? I don't know how to prove that. Is there an upper bound on the length of the cycle?
So you're saying that you believe that there is an upper bound?
I do.
Okay.
So
Countless such computations indicate not only that there is such an upper bound, but it's quite small, modest, with respect to the complexity of the function.
Sorry, just to make sure, like the bound depending on the degree, right? So you fix the degree, and that's and then the question is, right?
A fix of the function. So for the question that I asked, I'm asking for a particular map. So we have a particular map, and the question is there an upper bound on the length of a cycle for that map, for the slope function?
Okay. Mm-hmm.
And it's probably, I would anticipate that there is a bound that depends probably only on the degree or, some small amount of information about the map.
Okay, thank you.
Okay, let's say that that's enough for.
Can I quickly ask one more question? Sorry, but
yes.
So your program then also identified in this case 2 equators, right, and showed that
Correct.
this is a mating. I mean, I guess
Yes.
in 2 shared matings of 2 things. Okay. So just because the terminology is not uniform, I mean, to me an equator is like a curve, and the pre-image is one component and homotopic to the thing, which there are these sort of, let's say, more general versions of equators, the things that are called pseudo-equators. So this is equator really in a sense.
I'm using your definition.
Oh, okay, good. I just wanted to make sure. Yeah. Okay. Thank you.
I am explicitly using your definition.
Okay, thank you. So that makes it easier for me, obviously. Thanks a lot. Yeah.
Right.
Okay.
Right.
Thanks. Okay.
Right. So
but maybe
this is
sorry. Okay, but
yes?
maybe like.
So
I'm not sure if Daniel wanted to ask this, but does it also check if it's orientation preserving or not?
Say that again, please.
Or like, I mean, having the slope probably is not enough, Daniel, right? So you should also have like the like
two pieces have mapped into themselves.
I mean, you know, there's also this, you know, what I call anti-equators or what, which, you know, like, well, you have the Jordan curve at this orientation reversing to itself or what, and you know, I guess this would, you know, correspond to these anti-matings of Wolf-Jung. So I guess, I don't know, the question, Misha, that you may be asking is whether the program is well checking the correct orientation. Is that correct, Misha?
The program is checking orientation.
Okay, all right.
Okay, thank you. Okay.
Okay. So that's input method number one. Let's move on to input method number two. Input method number two is to draw the lift complex electronically. Let's go to this button that's labeled with draw, and we click on that, and this appears. We're going to draw the lift complex on this screen, on this white screen. The first thing to do is to draw some vertices. So we click the Add Vertices button, and now, once we've done that, whenever we left-click a vacant spot on this screen, a vertex appears. So we click, and we get a vertex. Click, 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 and we get vertices. That's enough vertices, so let's stop adding vertices. We click the Stop Adding Vertices button. This toggles between Add Vertices and Stop Adding Vertices. It's time to add edges. So we click the Add Edges button. Okay, now, if we click a vertex, now, I'll click this vertex, it turns red. That's telling us that this vertex is the first vertex of an edge that's about to be constructed. Now, if we click on another vertex, an edge appears between the two vertices. And let's do it again. Click on that one. And we have enough edges for now. Let's stop adding edges. Now, our vertices are movable. We can go to a vertex like this one, for example, and perform a left press. We press, but do not release. It's not a click, it's a press. And now we can move that vertex around. We can adjust where we want to put it. Let's try there. Oops. Okay, that's enough. Let's move this one now. Oh my.
So Walter, can I make a suggestion?
Yes.
I mean, you know, since time is running out here, can you maybe say more what your program can actually compute, right? I mean, I think we get the idea with the input, right? I mean, that you can, instead of specifying it in the previous case, you can give the input in this kind of graphical way.
Yes.
But you know, I would be more interested to see what else your program can actually do with the input.
Okay. Well, let's look at this. Here's a picture of the pullback map, or the map that we were considering before.
Yeah, so I mean, I would be very interested in how you actually compute the pullback map.
Yes. Okay. So here, let's first say what the picture means. We always have two halves, and the top half is telling us a fundamental domain for the action of the extended modular group liftables on the upper half plane. This is the pullback action of the extended modular group liftables on the upper half plane.
So how do you compute the group of liftables?
How do we compute the group of liftables? That is a discussion in itself.
All right, so fair enough.
But that would take up the rest of the time.
All right, fair enough, fair enough. Okay, so you compute the group of liftables, and then you have a
Yes.
fundamental domain.
That's the important, that's an all important step for almost all of these computations. We must be able to calculate liftables. Well, once we do that, then we can get a picture like this in this case. These are hyperbolic geodesics. We always get hyperbolic geodesics here. And when they're drawn with solid lines like this, as opposed to dotted lines, then that means that they are fixed point sets of reflections. There's a reflection about this geodesic A, and then there's a reflections, and so forth. Again, so this is a fundamental domain for the action of the extended modular group liftables. That is to be considered as always correct. Whereas below this, the second part is in general a guess. This is in general a guess. But in situations like this, in which case we always have a reflection group, the boundaries are fixed point sets of reflections, then this guess is probably always correct. And it is in this case, for example. So this means that geodesic A maps to geodesic A, and geodesic B maps to geodesic B, and C goes to C, D goes to D, and we have two geodesics up above mapping to A. So that indicates that infinity is mapping to the interior of this geodesic. So the program is saying that this Jordan domain is mapping to this Jordan domain, and in fact, conformally. So the pullback map restricted to the top Jordan domain conformally maps it to this bottom Jordan domain. And since these boundary geodesics are fixed point sets of reflections, the pullback map is gotten by the reflection principle. So the map on the entire upper half plane is gotten by reflecting what we have. So this describes.
Walter, sometimes the pullback map actually has critical points, right? So does your program also find these critical points?
In this case, there are none.
Well, but I mean, sometimes you do have critical points.
Sometimes there are critical points. Yes. Are you asking, does the program find them?
Yes.
Generally, no. Rarely. Once in a while, we sort of accidentally find a critical point, but in general, no.
But I guess, I mean, sometimes you could see this, right? If the boundary
correct.
If the boundary edges of the fundamental domain are labeled in like
correct.
I mean, once, then you could see this. I mean, that there must be.
Right. Yeah. Questions? It's possible that we could see that. I don't remember. I made up an example here with this picture. We have a 2x2 lattice map. We started with a 2x2 lattice map, and we blew up 4 of its edges. We blew up 2 horizontal edges and 2 vertical edges. And Mario and Misha and Anina proved that in this case there are no obstructions. What does the program have to say about this? It can draw the pullback map, and we get this picture. So do we get any? I don't see any critical points here either. But we have a remarkable fact that the imaginary axis maps to the imaginary axis, and the unit circle maps to the unit circle, and therefore the point of intersection maps to the point of intersection. I the pullback map is fixed point I. That does not, this is an unusual example. Well, okay, so I guess I'm past due and it's time to end.
Yeah, well, that's a bit unfortunate. I wish we had a little more time.
There's a lot more to talk about.
Yeah, exactly. So, well, so let me, let's first thank Walter for this kind of appetizer, I would say. And yeah, let's start the discussion here. I mean, I have many questions, but let's maybe give other people first a chance to ask something. So comments or questions?
I don't know, like, what is red curve in this picture? Like an obvious question.
Yeah, okay.
So what is red here?
Yeah,
Yes.
what does the red curve mean?
This is one of my favorite properties. So it says, it's telling us that the Jordan domain up here has a symmetry. Reflection about the red geodesic takes the Jordan domain here to itself. And it corresponds to reflection about this red geodesic. So reflecting about this geodesic corresponds to reflecting about this geodesic. And these two geodesics are actually equal. Remarkable fact. This is, you know, the Euclidean semicircle with radius square root of 2 centered at 1, which we can see by looking at this file. This no, not that file. This information down here says that the reflection corresponding to this geodesic has matrix 1, 1, 1, minus 1, and its image under the virtual endomorphism, the extension of the virtual endomorphism, is equal to itself. It's 1, 1, 1, minus 1. The pullback map, in other words, the pullback map commutes with this reflection. In this, just as it commutes with this reflection and this reflection. This is an unusual pullback map. It commutes with a dihedral group of order 8. We have a dihedral group of order 8 fixing I. So now the question is, where does this thing come from? This matrix has determinant -2. It's not even coming from PSL2Q. Why does it appear? How do you predict the occurrence of such things? This happens every once in a while, that a pullback map can have extra symmetries.
So maybe that's a very naive thing, but I mean, the map that you started out with has a lot of symmetries. Does that?
Yes.
I mean, so I mean, you know, let's say you draw, I mean, a certain map, or you know, your diagram, then the certain map that has a certain symmetry. Do you see that here? I mean, in the picture, you know, that you had here, or is that too naive?
No, I like that approach, but I don't know how to make that precise.
Okay.
So let me ask another question that goes back to some of the things that you said earlier. So, I mean, I can somehow see that if you slope map slopes to slopes, you get some non-trivial and useful information out of that. But what happens if a slope is actually mapped to a non-slope? How do you get any kind of information in this case? I mean, you mentioned this in one of the theorems that you showed.
How do you get information?
Well, can we go back to one of the slides that you showed in the very beginning? There was a theorem that related to, here. Right, so your extended half-space theorem.
Yes.
if a slope is mapped to the non-slope, right?
Yes.
This is one of the cases. Then
Yes.
how do you get any kind of information in this case?
In terms of what the image is, there's none.
Well, but
from the
but you talk about these deleted open intervals, right? So
Mhm. If this is not telling us anything about the image of this particular slope. It's just saying that we get this neighborhood that excludes negative reciprocals of slopes of obstructions.
yeah, so this is what I'm trying to understand. So if a slope is mapped to a non-slope, how do you get your open interval?
Oh, how do you get the information?
Yes.
You use the stabilizer of that particular slope. So, you seem to be asking, how does this proof go?
Well,
Yes.
yeah, sort of. In the case that the slope is mapped to a non-slope.
In the case of the slope is mapped to a non-slope, in that case, so we look at the stabilizer of that particular slope.
Mm-hmm.
Now, if the slope is mapped to the non-slope, that means that stabilizer is in the kernel of the virtual endomorphism. So that would say phi circle F is equal to F. And that information can be used to get information on a sequence. So we start with any half-space theorem excluded interval, and then apply the stabilizer to the slope that we use there.
Yeah,
and
I see. I get
see what you get. You get another interval that's not too far away from the interval with which you started, and then you iterate, and eventually these intervals begin to overlap.
Yeah, I see.
And there comes a point when they always overlap. So and then out to infinity, and so you get an entire interval on one side of your slope that you started with, and then you work the inverses of that stabilizer, and you eventually get an entire interval near on the other side of your slope.
Yeah, I see. Okay. So, I mean, there were many things that we couldn't discuss because we are out of time here. Is there some description of the mathematics behind your program?
Well,
is there some kind of user's guide or something like this that explains the mathematics?
Not really, no. We have these results. But how the program, there's no real description of the inner workings of the program.
Yeah, I mean, this is what I'm trying to get at. I mean, I would be very interested in understanding better the inner workings of your program.
Yes, no, sorry, that's I have no troubles writing up what has already been done here.
Well, look, I mean, because sometimes you said, I mean, okay, you have a guess, for example, for the computation of the Thurston pullback map in some cases, right? But you're not sure. So I would like to try to understand a little better what is exactly going on.
And that involves understanding reflections. Mm-hmm. So that's entirely any kind of progress that the program can make in that direction is involving understanding of reflections. So what reflections are liftable? And if the liftables inside the extended modular group form a reflection group, we're in great shape. That's the case when we can handle. That's what we looked at earlier.
I see.
Because it's easy to show that a reflection must map to a reflection under the virtual endomorphism. And then you get a fundamental domain. It's bounded by geodesics, which are fixed points of reflections, and the image reflections, and we're off.
I see. Okay. That at least gives some idea of what is going on.